Greetings to everyone. I am P. Evangelin Rajakumari, working as an assistant professor in Department of Mathematics, Bishop Heber College. In this video, I am going to explain the definition of Lebesgue outer measure and a theorem in the subject measure and integration. So, moving into the definition of Lebesgue outer measure, let A be a set in R and let In be a finite or countable collection of intervals of the form closed an, bn such that A is contained in or equal to union of In, where n varies from 1 to infinity. That is, In forms a finite or countable covering of A. The Lebesgue outer measure of A, or simply the outer measure of A, is denoted by m star of A and is defined as m star of A is equal to infimum of summation L of In, where the infimum is taken over all finite or countable collection of intervals In such that A is contained in or equal to union of In. So from this definition, it is noted that outer measure is a set function. Next, moving on to the theorem, it has 4 parts and we are going to prove it one by one. And the first subdivision is m star of A is greater than or equal to 0. Second portion is m star of pi equal to 0. Third one is m star of A is less than or equal to m star of B if A is contained in or equal to B. And the fourth one is m star of x equal to 0 for any x belongs to R. First portion, to prove m star of A is greater than or equal to 0, from the definition of the outer measure of A, we know that m star of A is equal to infimum of summation L of In. And In is an interval of the form closed an, bn. So length of this interval will be a non-negative number. So taking summation of L of In is also a non-negative number. And taking infimum of the set of all positive number is again a positive number. Therefore, we get m star of A is greater than or equal to 0. This proves the first subdivision. Second subdivision, we are going to prove that m star of pi equal to 0. So again, from the definition of outer measure of a set, m star of pi is equal to infimum of summation L of In, etc. Clearly, pi is contained in or equal to j1, which is equal to pi. Here j1 equal to pi, it has an interval of the form closed a, open a. When we take the length of this interval, you will be getting the value as 0. So again, pi is contained in or equal to union of n varies from 1 to infinity In, where In is an interval of the form closed an, open bn. Therefore, m star of pi is equal to infimum of L of j1, summation L of In, etc. So this L of j1 will be replaced by 0. And taking infimum of 0, summation L of In, etc. will give the result as 0. Therefore, we are getting it as m star of pi is equal to 0, which proves the second portion. So third subdivision is, we have to prove that m star of A is less than or equal to m star of B if A is contained in or equal to B. So for that, we are going to consider a finite or countable covering of A, In dash, In double dash, etc. Therefore, we get m star of A will be equal to infimum of summation L of In dash, summation L of In double dash, etc. Similarly, for the set B, we are considering the countable covering as Jn dash, Jn double dash, etc. So again, m star of B will be equal to infimum of summation L of Jn dash, summation L of Jn double dash, etc. And in the statement itself, it's given that A is contained in or equal to B, so that every countable covering of B is also a covering of A. So now we are going to consider two sets G and H in such a way that G is equal to summation L of In dash, summation L of In double dash, etc. Summation L of Jn dash, summation L of Jn double dash, etc. And the set H is represented as summation L of j n dash comma summation L of j n double dash comma etc. So while seeing these two sets, it's clear that H is contained in or equal to G. From the property of infimum, if A is contained in or equal to B means infimum of B is less than or equal to infimum of A. So using that property here, this value, that is H is contained in or equal to G, means it can be rewritten as infimum of G is less than or equal to infimum of H. That is M star of A is less than or equal to M star of B. So this proves the third portion. And the fourth one is to prove M star of X is equal to 0 for any X belongs to R. Okay, to prove this, we are going to consider an interval In of the form closed x comma x plus 1 by n, where n varies from 1 to 3 etc. And we note that when we take the length of this interval, we will be getting the value as 1 by n, where n varies from 1 to 3 etc. And this x is contained in or equal to In union pi union etc. That is, x is contained in or equal to In. Therefore, when we take M star, you will be getting it as M star of X equal to infimum of L of In comma etc, where n varies from 1 to 3 etc. That is, 0 is less than or equal to M star of X is less than or equal to L of In. That is, 0 less than or equal to M star of X less than or equal to this L of In is replaced by 1 by n. Therefore, we get that M star of X is equal to 0. So this proves the fourth portion. Hope you are all clear with the definition of Lebesgue outer measure and this theorem. Thank you for listening. Thank you.